On a clear night in late 2024, a telescope in Chile registers something new. The observation is automatic, logged by software that compares each image to the one before, searching for points of light that have moved. Most are known asteroids, already catalogued, already predicted. This one is not. It appears as a faint smudge against the background stars, unremarkable at first except that it is moving, and it is moving quickly. Within hours, other observatories confirm the detection. The object is designated C2224S1, a provisional name that will change as more data arrives. It is a comet, clearly outgassing, surrounded by a faint coma of sublimating ice. But the numbers attached to its motion are strange. The orbital elements do not close into an ellipse. The eccentricity exceeds 1. The velocity is too high. This means the object is not bound to the Sun. It is passing through. Astronomers begin to suspect what they are seeing only the third confirmed interstellar object ever detected in our solar system. The first, Oumuamua, arrived in 2017 tumbling and accelerating in ways no one fully understood. The second, 2I Borisov, appeared in 2019 behaving more like a typical comet, but still carrying the unmistakable signature of elsewhere. Now, in the closing months of 2024, something else has arrived. It will eventually be renamed 3I Atlas, after the survey that first caught its light. The realization spread slowly through the astronomical community, not with fanfare, but with the quiet adjustment of observation schedules, the reallocation of telescope time, the careful recalculation of approach parameters. There is no drama in this, only the steady accumulation of measurements, the patient work of determining what this visitor is and where it has been. 3I Atlas brightens as it approaches the Sun. This is expected. Comets always brighten as they warm, their frozen surfaces turning directly to gas in the vacuum of space, releasing dust and volatiles into a glowing envelope. But something about this one is unusual. The brightening curve does not match the predictions. It is too bright, or perhaps brightening too quickly, or perhaps responding to solar heating in a way that suggests its composition is different from the comets born here. No one knows yet. The data is still arriving. The object is still approaching. From Earth, it appears as a dim patch of light, visible only through large telescopes or sensitive cameras. It does not blaze across the sky. It does not inspire awe in casual observers. Most people on the planet do not know it exists. But in the archives of observatories, in the databases of orbital mechanics, in the minds of the few hundred humans who track such things, 3I Atlas occupies a unique position. It is a messenger from the space between stars, and it is here, now, moving through the inner solar system on a path it will trace only once. The object does not care that it is being watched. It does not care that its trajectory has been calculated, that its spectrum has been analysed, that its brightness has been measured and remeasured. It simply continues, pulled by the Sun's gravity into a hyperbolic arc, a curve that bends but does not close. It will swing past the Sun, absorb its warmth for a few brief months, and then depart, accelerating back toward the cold and the dark, never to return. Only took 4.5 billion years for us to notice when one arrives. The scientists observing it speak in careful language. They describe the orbital parameters, the estimated size, the spectral features. They note the uncertainties. They avoid speculation. But beneath the technical language, there is a quiet awareness that what they are observing is not just rare, it is a glimpse into the mechanics of galactic dispersal, the long, slow process by which matter is redistributed across the Milky Way. Every solar system sheds debris. Every forming planetary system ejects material into interstellar space. And occasionally, very occasionally, one of these exiles wanders close enough to another star to be seen. 3I Atlas is one such exile. It carries within it the frozen record of a star system that might be hundreds of light years away, that might no longer exist in the form it once did. The molecules locked in its ice were assembled in a molecular cloud, that collapsed long before our sun ignited. The dust grains embedded in its nucleus were forged in stellar winds or supernova remnants, swept into a disk around a young star, then flung outward when a planet grew large enough to scatter what remained. And now it is here, glowing faintly in Earth's telescopes, offering a brief chance to study the chemistry of elsewhere. The observations continue, night after night, as weather permits, as the object's position allows. The data accumulates in servers, in spreadsheets, in the collective effort of astronomers scattered across the globe. There is no certainty about what will be learned. There is no guarantee that the mystery of its unusual brightness will be solved, but the work proceeds, because the window is brief, and once 3i Atlas departs, it will be gone forever. From the comet's perspective, if a comet could have such a thing, the sun is just another star, no different from the countless others it has drifted past in its long journey through the galaxy. A brief flare of warmth, a temporary brightening, then back to the endless night. The word interstellar carries a weight that the mathematics behind it does not immediately reveal. It is not simply a label for something far away, or something rare, or something moving quickly. It describes an object whose origin lies outside the gravitational architecture of our sun, an object that was never part of the cloud that collapsed to form the solar system, never swept into orbit around our star, never shaped by the same processes that built the planets and moons and asteroid belt. 3i Atlas is interstellar because its velocity exceeds the escape velocity of the sun at its current distance. This is a precise, measurable fact. The orbital elements reveal an eccentricity greater than 1, a hyperbolic trajectory that opens outward rather than closing into an ellipse. No gravitational perturbation from the known planets can account for this. No close encounter with Jupiter or Saturn could have accelerated it to these speeds from a previously bound orbit. The conclusion is unavoidable. This object came from somewhere else. But where, exactly, remains unknown. Tracing the path of 3i Atlas backward through time is possible in principle. Astronomers can calculate its trajectory, account for the gravitational influences of the sun and planets, and project its motion into the past. The math is straightforward, but the uncertainties grow rapidly. Small errors in the measured velocity compound over millions of years. The gravitational tug of nearby stars, most of which have their own uncertain motions, becomes significant. After a certain point, the calculation dissolves into probability clouds, and the origin becomes unknowable. What can be said is this: 3i Atlas has been travelling through interstellar space for a very long time. Millions of years, at least. Perhaps tens of millions. During that time, it has been cold, far colder than anything on Earth. Colder than the surface of Pluto. Colder than the shadowed craters at the moon's poles. The temperature of interstellar space hovers just a few degrees above absolute zero, warmed only by the faint glow of starlight and the cosmic microwave background, the afterglow of the Big Bang itself. In this cold, chemical reactions effectively cease. Time, in a molecular sense, stops. The ice that makes up 3i Atlas water, methane, ammonia, carbon dioxide, and more complex organics has remained unchanged since it formed. No weathering, no erosion, no interaction with an atmosphere or a solar wind. The object is a frozen archive, preserving the conditions of its birth with almost no alteration. Only took crossing 100 trillion kilometers to deliver a sample we cannot touch. Comets born in our solar system, by contrast, are not pristine. They form in the same disk of gas and dust that gave rise to the planets, and they carry the chemical signature of that shared origin. Their ice reflects the composition of the solar nebula, a mixture dominated by water, with lesser amounts of carbon monoxide, methane, and ammonia, along with silicate dust and organic molecules. These comets have been warmed many times during previous passages near the Sun. Their surfaces have been altered by solar radiation. Their outer layers have been stripped away by sublimation. What remains is still ancient, still valuable, but not untouched. 3i Atlas is different. Its ice formed in a different molecular cloud, around a different star, under different conditions. The ratios of isotopes, different forms of the same element, with slightly different masses, may not match those found in solar system objects. The abundance of certain molecules may be higher or lower. The dust grains embedded in the ice may carry minerals that are rare here, or entirely absent. These differences, if they can be measured, offer a window into the diversity of planetary formation across the galaxy. They reveal that not all solar systems are alike, that the chemistry of star formation varies depending on the local environment, the mass of the collapsing cloud, the presence of nearby supernovae or stellar winds. Each interstellar visitor is a data point in a much larger story, the story of how matter is organized, processed, and redistributed on galactic scales. But measuring these differences is extraordinarily difficult. 3i Atlas is faint, distant, and moving quickly. Spectroscopy. The technique of splitting its light into component wavelengths to identify the molecules present requires long exposures on large telescopes. The signal is weak, the noise is high, and the comet is only visible for a limited time before it recedes beyond the reach of even the most powerful instruments. The astronomers observing it work within these constraints. They schedule time on telescopes in Chile, Hawaii, and space. They coordinate observations, share data, refine their models. They know they will not get everything. They know there will be unanswered questions, but they also know that this is the nature of the work, capturing what can be captured, measuring what can be measured, and accepting that the rest will remain unknown. Interstellar space is not empty, but it is sparse. The density of matter between stars is roughly 1 atom per cubic centimetre, far lower than the best vacuum achievable in a laboratory on Earth. In such an environment, collisions are rare. A comet like 3i Atlas can travel for millions of years without encountering anything larger than a dust grain. It drifts, essentially undisturbed, carried by the momentum it was given when it was ejected from its home system. This raises a quiet mystery: how common are such objects? For every interstellar comet that passes close enough to the Sun to be detected, how many more pass through the outer solar system unnoticed? How many cross the orbits of the outer planets without ever coming close enough to warm, to outgas, to reveal themselves? The answer is almost certainly many, perhaps thousands for every one we see, perhaps more. The galaxy, it turns out, is full of debris, not just stars and planets, but the remnants of planetary formation, the objects that were scattered, ejected, or otherwise lost during the chaotic early years of a solar system's evolution. These objects do not disappear. They continue to exist, travelling through the void, carrying with them the history of processes that occurred billions of years ago, light years away. 3i Atlas is one such remnant, a leftover, a cast-off, and yet, in its long journey through the galaxy, it has become something else. A traveller, a carrier of information, a link between one star system and another. It does not know this, of course. It simply continues, warming and brightening as the sun's gravity pulls it inward, responding to forces it has no awareness of, following a trajectory determined millions of years ago by events it cannot remember. Only took the invention of telescopes, digital cameras, and orbital mechanics to finally see what has always been passing by. The mathematics of determining whether an object is interstellar begins with position and time. 2 observations, separated by hours or days, reveal motion against the background stars. 3 observations allow the calculation of a preliminary orbit. 4 or more refine the uncertainties, narrowing the range of possible trajectories until a single solution emerges or fails to emerge, leaving only questions. For 3i Atlas, the first calculation suggests something unusual. The orbit does not close. Adjusting for errors does not change this. Adding more observations only strengthens the conclusion. The object is moving on a hyperbolic path, one that approaches the Sun, bends around it, and departs without ever looping back. The key parameter is orbital eccentricity, denoted by the letter E. For a circular orbit, E equals 0. For an ellipse, E lies between 0 and 1. For a parabola, the borderline case, where an object has just enough velocity to escape, E equals exactly 1. For a hyperbola, E exceeds 1, and the orbit is unbound. The object will leave the gravitational influence of the Sun and never return. 3i Atlas has an eccentricity greater than 1. Not by much, perhaps 1.01 or 1.02, depending on the precision of the measurements, but enough to confirm that it came from interstellar space and will return there. This number, this single decimal value, carries profound implications. It means the object's velocity, relative to the Sun, exceeds the local escape velocity by a measurable margin. It means that no combination of gravitational assists from the planets could have placed it on this trajectory from a previously bound orbit. It means that its origin lies elsewhere, in a region of space the Sun has never directly influenced. Calculating the exact path backward is more complicated. The motion must be integrated numerically, accounting for the gravitational pull of the Sun, the 8 planets, and even some of the larger asteroids if precision is required. Each body tugs on 3i Atlas as it passes, altering its trajectory slightly, and these perturbations must be modelled to reconstruct where the object was a year ago, a decade ago, a million years ago. The farther back the calculation extends, the larger the uncertainties become. A small error in the measured velocity, a fraction of a meter per second, propagates forward through the equations, becoming a larger error in position after 1,000 years, and an enormous error after 1,000,000. Eventually, the uncertainty envelope grows so wide that the object's past location becomes indeterminate. It could have come from this direction, or that direction, or any number of directions within a broad cone. Still, some constraints exist. The object's velocity relative to the local standard of rest, the average motion of stars in the Sun's neighbourhood, is not extraordinarily high. This suggests it has not travelled across the entire galaxy. It likely originated within a few hundred light years, possibly less. It may have been ejected from a young star system, or it may have drifted for so long that its original star has moved far from where it once was. Only took 4.5 billion years of planetary orbits to develop the math that proves something isn't one of ours. The process of confirming an interstellar origin is not instantaneous. It requires patience, repeated observations, and the gradual reduction of uncertainties. Early reports are cautious. The object is described as potentially interstellar or consistent with an unbound orbit. Only after weeks of data collection, after the trajectory has been measured with sufficient precision, does the language shift. The designation changes. The object is confirmed. For 3i Atlas, this confirmation arrives in late 2024 after enough observatories have tracked its motion to eliminate alternative explanations. The International Astronomical Union formally recognizes it as the third interstellar object detected passing through the solar system. The 3i prefix replaces the provisional Comet designation. The name Atlas remains, honouring the survey that first spotted it. There is no ceremony, no announcement beyond a technical circular distributed to professional astronomers. The discovery does not make headlines, except in specialised publications. Most of the world remains unaware. But within the small community of researchers who study such things, the confirmation is significant. 3 detections in 7 years suggest that interstellar objects are not as rare as once thought. It suggests that the galaxy is thick with such wanderers, and that our instruments are only now becoming sensitive enough to see them. The hyperbolic trajectory of 3i Atlas also reveals something about its velocity before entering the solar system. In the reference frame of the Sun, it is moving at roughly 30 to 40 kilometers per second fast, but not extraordinarily so. This is comparable to the orbital speeds of the outer planets, and to the typical velocities of stars in the galactic disk. It suggests the object has been drifting for a long time, its motion gradually randomized by the weak gravitational influences of passing stars, until by chance it wandered into the Sun's gravitational well. The encounter with the Sun accelerates it temporarily. As 3i Atlas falls inward, it gains speed, much like a ball rolling down a hill. At its closest approach, its perihelion, it will be moving at perhaps 60 or 70 kilometers per second relative to the Sun. Then, as it climbs back out of the gravitational well, it will slow again, eventually returning to approximately the speed it had when it arrived. The Sun gives the object a brief boost, then takes it back. The net effect is a deflection, a change in direction, but not a significant change in speed. This is the nature of hyperbolic encounters. The object borrows energy temporarily, uses it to bend its path, then returns it as it departs. The trajectory is smooth, continuous, governed entirely by gravity and inertia. There are no sudden changes, no unpredictable accelerations, or at least, there should not be. Oumuamua, the first interstellar object, complicated this picture. As it receded from the Sun, it accelerated slightly more than gravity alone could explain. The effect was small but measurable, and it defied easy explanation. Was it outgassing, like a comet, even though no coma was detected? Was it shaped in such a way that radiation pressure from sunlight could push it? Was it something else entirely? The mystery remains unresolved. For 3i Atlas, the question is whether a similar anomaly will appear. So far, the trajectory matches predictions. But the object is still approaching the Sun, still warming, still in the phase where surprises could emerge. The astronomers tracking it watch carefully, measuring its position night after night, checking for deviations. They do not expect drama, but they also know that interstellar objects have already proven themselves capable of unexpected behavior. Only took 2 previous visitors to teach us that we do not yet understand what we're seeing. The orbital calculations continue, the data accumulates, the trajectory sharpens, and 3i Atlas continues inward, indifferent to the fact that its path has been predicted, that its future has been mapped, that somewhere on Earth, in a database, its position for the next 6 months exists as a series of coordinates, waiting to be compared against reality. The ice that composes much of 3i Atlas has never been touched by our Sun's warmth. This is not a poetic statement, but a literal one. The molecules locked within its nucleus water, methane, ammonia, carbon monoxide, and more complex organics condensed from a molecular cloud that existed long before the solar system formed, or they froze onto dust grains in the protoplanetary disk of another star entirely. Either way, they have spent millions of years at temperatures hovering just a few degrees above absolute zero, preserved in a state of nearly perfect dormancy. In interstellar space, the ambient temperature is approximately 2.7 Kelvin, the residual warmth of the Big Bang diluted and redshifted over 13.8 billion years of cosmic expansion. There is no atmosphere to trap heat, no nearby star to provide illumination, no mechanism for warmth except the faint glow of distant starlight and the occasional impact of cosmic rays. At such temperatures, thermal motion slows to a crawl. Atoms vibrate in place but do not break their molecular bonds. Chemical reactions, which depend on particles colliding with sufficient energy to rearrange, become vanishingly rare. Time, in a chemical sense, freezes. This means the ice in 3i Atlas is ancient not only in years but in structure. It has not melted and refrozen. It has not sublimated and redeposited. It has not been churned by tidal forces or heated by radioactive decay. It is, as nearly as anything in the universe can be, unchanged since the moment it formed, a molecular snapshot of conditions that existed around another star, in another system, at a time when Earth may not yet have existed. The composition of this ice is not identical to that found in comets born in our solar system, though the differences may be subtle. Water ice dominates in both cases, but the ratios of other volatiles, methane, ammonia, carbon dioxide, methanol can vary depending on the temperature and pressure at which they condensed. Colder environments favour the retention of more volatile species, Warmer environments allow lighter molecules to escape before freezing occurs. The exact mixture becomes a signature of the local conditions during formation. For interstellar objects, these signatures can be wildly different. Some molecular clouds are enriched in carbon monoxide, others in ammonia. Some are seeded with dust from recent supernovae, carrying isotopes that are rare elsewhere. The star around which the object formed its mass, its temperature, its radiation output also leaves an imprint. A massive, hot star evaporates volatiles more efficiently than a cooler, smaller one. A star with a strong stellar wind blows away lighter elements before they can be incorporated into forming comets. 3I Atlas carries all of this information, encoded in ratios and abundances that can, in principle, be measured. But measuring them requires spectroscopy, the analysis of light passing through or reflecting off the comet's coma, the cloud of gas and dust that surrounds the nucleus as it warms, and that analysis requires the comet to be outgassing, to be releasing its volatiles into space where they can be observed. Only took a close approach to a star to finally reveal what has been hidden for eons. As 3I Atlas moves closer to the Sun, the ice begins to respond. At first, the warming is negligible. Beyond the orbit of Jupiter, the sunlight is too weak to raise the surface temperature significantly. The comet remains dormant, dark, essentially invisible except as a faint reflected glimmer. But as it crosses the orbit of Mars, the temperature climbs. Water ice, still too cold to sublimate, begins to soften. More volatile species carbon monoxide. Methane begin to transition directly from solid to gas, a process called sublimation, which occurs without passing through a liquid phase. This outgassing is not uniform. It depends on which part of the nucleus is illuminated, on the composition of the surface, on whether the ice is pure or mixed with dust and rock. Some areas may be covered by a dark, insulating layer of non-volatile material silicates, carbon-rich organics that prevent sublimation. Other areas may be pure ice, exposed and active, jetting gas into space as soon as the temperature rises above the threshold. The gas forms a coma, an envelope that surrounds the nucleus and extends outward for thousands or tens of thousands of kilometers. This coma is not dense. The pressure is far lower than any vacuum chamber on Earth, but it is enough to scatter sunlight, making the comet visible. Dust grains, lifted by the escaping gas, add to the brightness. The tail, if one forms, points away from the sun, pushed by the solar wind and radiation pressure. For astronomers, the coma is a treasure. It contains the molecules that were locked inside the nucleus, now free and detectable. Spectroscopy can identify them by their absorption or emission lines, the unique fingerprints each molecule leaves in the spectrum of sunlight passing through the gas. Water shows up as broad features in the infrared. Carbon monoxide appears in the ultraviolet. Methane, ammonia, hydrogen cyanide, each has its own signature. But there is a complication. The molecules in the coma are not necessarily the same as those in the ice. Many are fragments, broken apart by solar ultraviolet radiation almost as soon as they are released. Water molecules, for example, are quickly photodissociated into hydrogen and oxygen. Carbon dioxide breaks into carbon monoxide and oxygen. The spectrum reveals not the original composition, but a mixture of parent molecules and their photochemical products. Disentangling these requires modelling, comparing the observed spectrum to predictions based on different assumed compositions, iterating until a match is found. The process is uncertain, sensitive to assumptions about the comet's activity level, its rotation, its surface properties. Different teams, analysing the same data, may arrive at slightly different conclusions. For 3I Atlas, early spectroscopic observations suggest the presence of water, as expected, along with carbon-based molecules, possibly carbon monoxide, possibly cyanogen or other organic species. The exact ratios are still being determined. The data is noisy. The signal is weak. but the preliminary results hint at a composition that is not radically different from solar system comets. Though subtle differences may exist, this is both reassuring and puzzling. Reassuring, because it suggests that the basic processes of ice formation, condensation from gas, incorporation into planetesimals, freezing at low temperatures are universal, not unique to our solar system. Puzzling, because it raises the question of how much variation exists across the galaxy. If all comets, regardless of origin, have similar compositions, what does that say about the uniformity of molecular clouds, or the constraints of chemistry in cold environments only took the light from a distant fusion reactor to unlock secrets frozen when another star was young? The ice continues to sublimate as 3I Atlas approaches. The coma brightens, the outgassing rate increases, and somewhere in the stream of data pouring into telescopes, in the wavelengths of light absorbed and emitted, lies the chemical signature of a place no human will ever visit, written in molecules that have travelled farther than any spacecraft we have built. The brightness of 3I Atlas does not behave as predicted. This is noticed early, in the first weeks of observation, when astronomers compare the measured magnitude, the apparent brightness as seen from Earth, to the expected value based on standard comet models. The discrepancy is small at first, within the range of normal variation, but it persists, and as more data accumulates, the pattern becomes clear. The comet is brighter than it should be, given its distance from the Sun and its estimated size. Brightness, for a comet, is a function of several variables. The most important is distance from the Sun, which determines how much sunlight strikes the nucleus and how much gas and dust is released. Closer to the Sun means more heating, more outgassing, more material in the coma to scatter light. This relationship follows a predictable curve, typically modelled as a power law. Brightness increases as some function of decreasing distance, usually proportional to the inverse square or inverse cube of the distance, depending on whether the comet is already active or just beginning to warm. For 3I Atlas, the observed brightness increases faster than this standard model predicts. At a given distance, the comet is several times brighter than expected. This could mean several things. It could mean the nucleus is larger than initially estimated, with more surface area available for outgassing. It could mean the surface is unusually rich in volatiles, releasing gas at a higher rate than typical comets. It could mean the composition is different, with more carbon monoxide or other highly volatile species that sublimate at greater distances from the Sun. Or it could mean something else entirely, a structural anomaly, a fragmentation event, or a process not yet accounted for in the models. The uncertainty is compounded by the fact that the nucleus itself is not directly visible. What astronomers observe is the coma and, if present, the tail, the light scattered by gas and dust surrounding the nucleus. The nucleus is buried within, too small and too faint to resolve even with the most powerful telescopes. Its size must be inferred indirectly from the total amount of outgassing, the brightness of the coma, and assumptions about the fraction of the surface that is active. These assumptions are often wrong. Some comets have nuclei that are almost entirely inert, covered by a thick crust of non-volatile material with only a few small active areas. Others are fresh and pristine, with ice exposed over much of the surface. The difference can be a factor of 10 or more in outgassing rate, and therefore in brightness. Without knowing which type 3I Atlas is, predictions are necessarily rough. Only took one visitor from another star to remind us how much we assume about ice we've never touched. One possibility is that 3I Atlas is fragmenting. Comets do this occasionally, splitting into two or more pieces as thermal stresses or rotational forces overcome the weak gravitational binding of the nucleus. When fragmentation occurs, the total surface area increases and the outgassing rate jumps. The comet brightens suddenly, sometimes by several magnitudes, before gradually fading as the fragments disperse or deplete their volatiles. Observers watch for signs of this. They examine images carefully, looking for multiple condensations within the coma, for asymmetries in the brightness distribution, for anything that might indicate the nucleus is broken apart. So far, the evidence is inconclusive. The comet appears as a single diffuse patch, without obvious structure, but the resolution is limited, and small fragments might not be distinguishable from the background glow. Another possibility is compositional. If 3I Atlas formed in a colder environment than typical solar system comets, it might retain a higher fraction of highly volatile ice species like carbon monoxide, methane, or nitrogen, which sublimate at much greater distances from the Sun than water ice. These volatiles begin outgassing while the comet is still far from the inner solar system, producing activity and brightness at distances where water-dominated comets remain dormant. This would fit with the interstellar origin. Different molecular clouds have different temperatures, and the temperature at which ice condenses determines which molecules are incorporated. A cloud that is colder by even 10 or 20 degrees can produce ice with a significantly different composition, favouring the retention of the lightest, most volatile species. But measuring this directly is difficult. The spectroscopic signatures of carbon monoxide and methane are faint and often masked by stronger features from water and its dissociation products. Detecting them requires observations in the ultraviolet or infrared, wavelengths that are partially or entirely absorbed by Earth's atmosphere. Space-based telescopes are needed, and time on such instruments is precious and heavily oversubscribed. Some observations have been scheduled, data is being collected, but the analysis takes time and the results are not yet public. The brightness anomaly remains, for now, unexplained. There is also the possibility that the anomaly is not an anomaly at all, that the models are simply inadequate. Comet brightness is notoriously difficult to predict, even for well-studied objects. Each comet is unique, with its own rotation rate, its own surface properties, its own history of solar heating. Standard models capture the average behaviour, but individual comets often deviate, sometimes by large factors. 3I Atlas may simply be another example of this variability, no more mysterious than any other comet that has surprised observers by brightening unexpectedly. Yet the fact that it is interstellar adds weight to the anomaly. If 3I Atlas behaves differently from solar system comets, that difference becomes significant, a potential clue to the conditions under which it formed. If it behaves the same, that uniformity is also significant, suggesting that the processes of comet formation are not strongly dependent on the details of the parent star or molecular cloud. Either way, the brightness is information. It tells a story, even if that story is not yet fully readable. Only took 3 interstellar visitors to begin asking whether our models of ice and dust apply beyond the Sun's children. The observations continue. Photometry. The measurement of brightness over time is performed nightly, weather permitting, by multiple observatories. The data is shared, cross-checked, calibrated to standard systems. Slowly, the light curve takes shape a plot of brightness versus time, or brightness versus distance from the Sun, revealing the pattern of how 3I Atlas responds to warming. The curve is steep, steeper than most. This confirms that the brightening is real, not an artifact of measurement error or atmospheric conditions. The comet is genuinely more active, or more reflective, or larger, or something than initial estimates suggested. What remains unknown is whether this brightness will continue to increase as the comet approaches perihelion, or whether it will plateau, or whether something unexpected will happen, a sudden surge, a fragmentation, a return to dormancy as volatile rich layers are exhausted and a less active surface is exposed. The telescopes watch, the data accumulates, and 3I Atlas, unaware of the scrutiny, continues to brighten, continues to release gas and dust into the vacuum, continues inward toward the Sun, carrying its unresolved mystery with it. In 2017, an object designated Oumuamua passed through the inner solar system on a trajectory that would take it back into interstellar space. It was the first confirmed visitor from beyond, detected by the Pan-STARRS telescope in Hawaii, as it was already receding from the Sun. By the time astronomers realized what they were observing, the object was too distant for detailed study. Only a handful of observations were possible before it faded beyond the reach of even the largest telescopes. What those observations revealed was puzzling. Oumuamua appeared to be elongated, perhaps cigar-shaped or disc-like, tumbling end over end as it travelled. It showed no sign of a coma, no outgassing, no tail, none of the features typical of a comet. Spectroscopically, it resembled an asteroid, its surface reddish and presumably covered in organic compounds processed by cosmic rays. Yet as it receded, careful measurements of its trajectory revealed a small but unmistakable acceleration, a deviation from the path predicted by gravity alone. This acceleration was not large, a fraction of a percent, but it was real, detected independently by multiple teams analysing the same astrometric data. Something was pushing Oumuamua, and the most straightforward explanation was outgassing jets of sublimating ice, providing a gentle thrust, like a natural rocket engine. But if the object was outgassing, why was no coma detected? Why were there no spectroscopic signatures of water or other volatiles? Why did it look like an asteroid? Various explanations were proposed. Perhaps the outgassing was pure nitrogen, which would not produce a visible coma. Perhaps the object was covered by a thick insulating crust, with only small vents releasing gas. Perhaps it was shaped in such a way that radiation pressure from sunlight photons bouncing off its surface could account for the acceleration. Or perhaps it was something more exotic, a fragment of a disrupted planet, a shard of hydrogen ice, even, in the most speculative proposals, an artificial object. None of these explanations are entirely satisfying. Each requires assumptions that stretch the boundaries of what is considered plausible, and so Oumuamua remains, in the astronomical literature, an unresolved anomaly, a data point that does not fit comfortably into existing categories. Only took one mystery object to teach us that interstellar does not mean understandable. 3i Atlas invites comparison. Like Oumuamua, it is interstellar, hyperbolic, never to return. But unlike Oumuamua, it behaves, at least superficially, more like a conventional comet. It has a coma. It is outgassing. Its spectrum shows the signatures of water and carbon-based molecules. It brightens as it approaches the sun, following a pattern that, while anomalous in degree, is not anomalous in kind. It is, in most respects, what a comet should be. Yet the memory of Oumuamua lingers. Astronomers watching 3i Atlas are alert for deviations, for unexpected accelerations or decelerations, for anything that might suggest forces beyond simple gravity and outgassing. So far, none have been detected. The trajectory matches predictions, but the object is still approaching perihelion, still in the phase where surprises could emerge. The lesson of Oumuamua is that interstellar objects can defy expectations, and that assumptions about their behaviour should be held lightly. The second interstellar object, 2I Borisov, detected in 2019, offered a contrasting case. Borisov was clearly a comet from the moment it was discovered. With a well-developed coma and a tail, its spectrum showed carbon monoxide in unusually high abundance, suggesting a composition enriched in volatiles, possibly due to formation in a colder environment than typical solar system comets. But otherwise, Borisov behaved predictably. Its trajectory followed a smooth hyperbolic arc, with no anomalous accelerations. Its brightness varied in a way consistent with rotational modulation and changing outgassing rates. It was, in essence, a normal comet that happened to come from somewhere else. Borisov's normalcy was, in its own way, as informative as Oumuamua's strangeness. It demonstrated that not all interstellar visitors are exotic, that some are simply comets, indistinguishable in most respects from those born in our solar system. It suggested that the processes of comet formation, the condensation of ice, the accretion of dust, the incorporation into planetesimals are not unique to any one star, but are universal features of planetary system evolution. 3i Atlas, so far, seems to fall somewhere between these two extremes. It is more active than Oumuamua, less compositionally extreme than Borisov. Its brightness anomaly is notable but not unprecedented. It is, perhaps, the most ordinary of the three interstellar objects detected so far, and yet that ordinariness is itself data, a point of reference against which future discoveries can be measured. Only took 3 visitors to begin sketching the outlines of a population we are only starting to see. The question of whether 3i Atlas will exhibit any Oumuamua-like behaviour remains open. As it continues to warm, as its outgassing rate increases, subtle forces begin to play a larger role in its motion. The thrust from jets of sublimating ice, though weak, can accumulate over time, causing deviations from a purely gravitational trajectory. These deviations are typically small, measured in meters per second of velocity change over weeks or months, but they are detectable, if the observations are precise enough. For a comet with a well-developed coma, such non-gravitational accelerations are expected. They are, in fact, routinely included in orbit determination, modelled as forces proportional to the outgassing rate and directed away from the Sun. The challenge is distinguishing between normal cometary behaviour and something unusual, between a gentle push from sublimating ice and an acceleration that cannot be explained by known processes. So far, 3i Atlas shows no signs of the latter, but the data is still being collected, the orbit is still being refined, and the astronomers tracking it remain watchful, aware that interstellar objects have already proven themselves capable of surprise. The shadow of Oumuamua extends forward in time, shaping expectations, colouring interpretations. Every measurement of 3i Atlas is, in some sense, compared to that first enigmatic visitor. Every anomaly, real or suspected, raises the question, is this another Oumuamua, or is it something we already understand? The answer, as always, will come slowly, emerging from the accumulation of data, the careful analysis of trajectories, the patient work of distinguishing signal from noise, and in the background, unspoken but present, is the awareness that these are only the first few, that the galaxy contains billions of such objects, and that our detection of them is just beginning. That what we learn from Oumuamua, from Borisov, from 3i Atlas, is preliminary, the opening notes of a much longer composition, one that will take decades or centuries to hear in full. The comparison continues, the data accumulates, and 3i Atlas, indifferent to its predecessors, continues inward, carrying with it the possibility of confirmation or contradiction, of the familiar or the strange. Before 3i Atlas entered the solar system, it drifted, not for years or centuries or millennia, but for millions of years, perhaps tens of millions, moving through the space between stars at a velocity of a few dozen kilometers per second. This is fast by human standards, fast enough to cross the width of Earth in half a second, but slow in the context of the galaxy. At such speeds, crossing the distance between neighbouring stars takes hundreds of thousands of years. Crossing the distance between spiral arms takes millions. During this time, nothing happened. The comet did not warm, it did not outgas, it did not interact with anything larger than the occasional dust grain or hydrogen atom. The density of interstellar space is so low, roughly 1 atom per cubic centimetre, that collisions are vanishingly rare. A comet the size of 3i Atlas, perhaps a few kilometres across, could travel for 1 million years without encountering a single object large enough to register an impact. The environment is not entirely empty, but it is profoundly still. Starlight bathes the object, but faintly. The accumulated glow of billions of distant suns reduced to a dim background luminescence, far too weak to warm the surface above a few degrees Kelvin. Cosmic rays, high-energy particles from supernova remnants and other violent events strike the nucleus occasionally, breaking molecular bonds, creating free radicals, gradually altering the surface chemistry. But the rate of change is glacial, measured in atomic displacements per century, insignificant over the timescales of a single human life, but accumulating, slowly, over millions of years. The comet tumbles as it travels, its rotation set by whatever event ejected it from its home system. Perhaps it was a close encounter with a giant planet, the gravitational torque imparting angular momentum as it was flung outward. Perhaps it was a collision with another planetesimal, the impact sending fragments spinning in different directions. Whatever the cause, the rotation persists, unaltered by any external force. In the absence of atmosphere or tidal forces, there is nothing to slow it down, nothing to change its spin axis. It simply continues, turning once every few hours or days or weeks, its orientation slowly precessing as the gravitational influences of passing stars tug gently on its asymmetric mass distribution. Only took the width of the galaxy to turn cosmic violence into cosmic stillness. The trajectory of 3i Atlas through the galaxy is not straight. Gravity bends it, constantly. Every star it passes exerts a pull, however faint, deflecting the comet slightly from its path. Most of these deflections are tiny, fractions of a degree, but over millions of years they accumulate. The comet's path curves and wanders, a long, smooth arc through the gravitational landscape of the Milky Way. It may have passed within a light year of dozens of stars, within a parsec of hundreds, each encounter leaving a small mark on its trajectory, nudging it this way or that. There is no way to reconstruct this path with certainty. The gravitational field of the galaxy is too complex, too dependent on the positions and motions of individual stars, most of which are not precisely known. The calculation dissolves into uncertainty after a few million years, the possible paths branching into a cloud of probabilities. Somewhere in that cloud is the star around which 3i Atlas formed, the place where its ice condensed and its nucleus accreted. But where, exactly, cannot be determined. What can be said is that the comet has travelled far. The galaxy rotates, and stars orbit the galactic centre at different speeds depending on their distance from the core. The Sun, located about halfway out in the disk, completes an orbit roughly every 230 million years. Stars closer to the centre move faster, stars farther out move slower, over millions of years. The relative positions of stars change dramatically. Neighbours drift apart, clusters dissolve. The configuration of the local stellar neighbourhood is constantly rearranging, like a slow, vast dance with no fixed partners. 3i Atlas, adrift in this dance, has likely moved through regions of varying stellar density. It may have passed through the plane of the galactic disk multiple times, where the density of stars and gas is higher. It may have wandered above or below the plane, into regions where stars are sparse and the distance between them grows. Each environment presents different risks, different probabilities of close encounters, different radiation environments, different chances of capture by a passing star's gravity. Yet it remained free. It was not captured. It was not destroyed. It simply continued, carried by its momentum, slowly losing speed relative to the local rest frame as it climbed out of gravitational wells and was deflected by passing stars, but never losing enough speed to be bound, never encountering a star closely enough to be pulled into orbit or torn apart by tidal forces. This survival is not remarkable in itself. The galaxy is vast, and the probability of any given object colliding with a star or being captured is extraordinarily low. But it is worth noting that for every interstellar object like 3i Atlas that has survived its journey, there are likely many others that have not objects that strayed too close to a star and were consumed, or were captured into highly eccentric orbits and later ejected again, or fragmented under the stress of a close encounter and dispersed into undetectable debris. Only took a galaxy full of near misses to deliver one intact visitor to our doorstep. During its long drift, 3. Atlas was entirely invisible. No telescope from Earth or anywhere else in the solar system could have detected it. It was too far, too small, too cold, too dark. Its surface, covered in ice and perhaps a layer of irradiated organic material, reflected no measurable light. It emitted no heat, it made no sound, produced no signal, left no trace. It was, for all practical purposes, non-existent, a phantom wandering through a universe that did not know it was there. This is the fate of most interstellar objects. They drift unseen, their existence inferred only statistically, from the handful that happen to pass close enough to a star to be warmed, to outgaze, to become briefly visible. For every one we detect, there are likely thousands or millions that pass through the outer reaches of the solar system unnoticed, too distant to interact with the sun, too cold to produce any activity, invisible against the background of stars. The galaxy, in this sense, is full of ghosts, objects that exist but cannot be seen, that move but leave no trail, that carry information but have no means of transmitting it. They are the remnants of planetary formation, the leftovers of 1 billion star systems, scattered across the disk and halo of the Milky Way, slowly mixing, slowly diffusing, until the distances between them are so great that encounters become rare even on cosmic timescales. 3i Atlas was one such ghost until very recently. Its long isolation ended only when it wandered, by chance, into the gravitational influence of a star, our star, and began the final descent that would make it visible, briefly, before it returned to the dark. The transition from invisibility to visibility is not abrupt, it is gradual. A slow warming as the sunlight intensifies, a gradual onset of sublimation as the surface temperature rises above the threshold for the most volatile ices. By the time 3i Atlas was detected, it had already been warming for months or years, already begun the process that would transform it from a dark, inert lump of ice into an active comet with a coma and, eventually, a tail. But for the vast majority of its existence, it was not this. It was simply cold, dark, silent, drifting through a galaxy that took no notice of its passage, carrying within it the frozen memory of a place and time that will never be known. There is much about 3i Atlas that cannot be seen. The nucleus, buried within the coma, remains unresolved, a point source, or perhaps not even that, lost in the diffuse glow of the surrounding gas and dust. Its exact size is unknown. Estimates place it somewhere between a few hundred meters and a few kilometers in diameter, but this range is wide, and the true value could lie anywhere within it, or even outside it if the assumptions about surface reflectivity and outgassing efficiency are incorrect. The shape of the nucleus is also unknown. Is it spherical, elongated, irregular? Does it resemble a potato, a peanut, a fractured boulder? Cometary nuclei observed up close by spacecraft have shown remarkable diversity. Some are nearly round. Others are contact binaries, 2 lobes joined by a narrow neck. Still others are jagged and asymmetric, shaped by collisions, outgassing, or the stresses of formation. Without a spacecraft visit, which is impossible for an object moving on a hyperbolic trajectory through the inner solar system, the shape of 3i Atlas remains a matter of speculation. The rotation rate is similarly uncertain. Observations of brightness variations over time could, in principle, reveal the rotation period, the time it takes for the nucleus to complete one turn, but the signal is complicated by changes in outgassing, by the irregular distribution of active areas on the surface, by the viewing geometry as the comet moves relative to Earth. The brightness fluctuates, but disentangling rotational modulation from other effects requires extended monitoring, careful photometry, and analysis that is still ongoing. Even the surface properties are largely unknown. Is the nucleus dark or bright? Cometary surfaces are typically very dark, with reflectivities lower than coal, their ice mixed with or covered by non-volatile carbonaceous material that has been processed by radiation and heating. But some comets have brighter patches, areas where fresh ice has been recently exposed by outgassing or impacts. Without high-resolution imaging, the surface of 3i Atlas remains a blank, a theoretical construct inferred from models and analogies with other comets, but not directly observed. only took 4.5 billion years of astronomy to learn how much we miss when we cannot send a probe. The interior of the nucleus is even more inaccessible. What lies beneath the surface is the ice homogeneous, or layered. Are there pockets of highly volatile material carbon monoxide, methane trapped within a matrix of water ice? Are there voids, fractures, regions of different density or composition? These questions matter because they determine how the comet will behave as it warms, how quickly it will outgas, whether it might fragment under thermal or rotational stress. Models suggest that cometary interiors are heterogeneous, built up from smaller icy particles that accreted gently in the outer regions of a protoplanetary disk, preserving their individual identities rather than melting and mixing. This would produce a rubble pile structure, loosely bound by gravity and weak cohesive forces, with porosity that could be as high as 70 or 80% more empty space than solid material. Such a structure would be fragile, vulnerable to disruption, but also insulating, protecting deeper layers from solar heating and preserving pristine ice that has never been warmed. But these are generalizations based on observations of solar system comets and theoretical considerations. Whether they apply to 3I Atlas is unknown. The object may be denser, more cohesive, less porous. It may have a different internal structure, shaped by different conditions during formation, or altered by a longer exposure to cosmic rays during its interstellar journey. Without seismic data, or penetrating radar, or direct measurement of mass and density, the interior remains conjectural. The composition, too, is only partially known. Spectroscopy reveals the molecules present in the coma, the gas that has been released from the nucleus and is now surrounding it. But this is not a complete inventory. Some molecules may be present in the ice but not detected in the coma, either because they do not sublimate readily at the current distance from the Sun, or because they are photodissociated too quickly to produce a measurable signal. Others may be trapped in the dust grains that are lifted off the surface along with the gas, locked in a form that is not accessible to remote observation. The isotopic ratios, the relative abundances of different isotopes of hydrogen, oxygen, carbon, nitrogen are particularly valuable because they provide clues about the temperature and environment in which the ice formed. But measuring isotopic ratios requires high-resolution spectroscopy, long integration times, and, ideally, observations at wavelengths that are blocked by Earth's atmosphere. Some of this data may be collected. Eventually, if enough telescope time can be secured and the comet remains bright enough, but there are no guarantees. Only took crossing light years to arrive at a moment when the tools to study you might not be available. The dust in the coma is another unknown. Particles of silicate, carbon, organic compounds lifted from the surface by the escaping gas, carried outward into space, gradually dispersed by radiation pressure and the solar wind. The size distribution of these particles, their composition, their structure, all carry information about the conditions in the protoplanetary disk where they formed. But dust is difficult to study remotely. It scatters light, and the way it scatters depends on particle size, shape, and refractive index. Modelling this scattering to infer the properties of the dust requires assumptions, and those assumptions are often uncertain. Some information can be gleaned from polarimetry measuring the polarization of the scattered light, which depends on particle properties. Some can come from infrared observations, which reveal the thermal emission from warm dust grains, but the interpretation is indirect, and different models can fit the same data. The dust, like so much else about 3I Atlas, remains partially hidden, revealed only through proxies and inferences. There is also the question of what has been lost. 3I Atlas has been outgassing since it entered the inner solar system, releasing gas and dust that are now dispersed along its orbital path. This material is gone, no longer part of the nucleus, and it represents information that has been erased. The comet we observe now is not the same comet that crossed the orbit of Mars or the orbit of Jupiter. It has shed mass, changed its surface, exposed new layers. The pristine ice that existed when it was still in interstellar space is, at least in the outermost layers, no longer pristine. This is an unavoidable consequence of observation. To see a comet, it must be active. To be active, it must be warm. To be warm, it must be close to a star. And being close to a star means losing material, altering the very thing we are trying to study. The act of observation changes the object. The data we collect is data about a comet in the process of transformation, not data about the comet as it once was. Only took the light that makes it visible to also make it unreachable. And then there is the question of time. The window for observing 3i Atlas is brief. A few months, perhaps a year, during which the comet is bright enough and well placed enough for detailed study. After that, it will recede, fading as it moves away from the sun, its outgassing declining, its coma shrinking until it becomes too faint to observe even with the largest telescopes. The opportunity to gather data is limited, and what is not captured now will be lost forever. Astronomers are acutely aware of this. They schedule observations aggressively, coordinate across institutions and countries, share data as quickly as it can be processed. But there are limits. Telescope time is finite. Weather interrupts. Instruments fail. The comet does not pause for technical difficulties or cloudy skies. It continues on its trajectory, indifferent to the constraints of those trying to study it. So the data that exists, when the observations finally end, will be incomplete. It will be enough to answer some questions, but not all. It will reveal patterns, but leave mysteries. It will confirm some hypotheses and complicate others, and the astronomers will work with what they have, extracting as much as possible, knowing that the rest, the majority, perhaps will remain unknown. 3i Atlas will depart carrying its secrets with it, sealed again in ice, invisible, unreachable, drifting back into the void from which it came. The object now designated 3i Atlas was not always interstellar. It formed somewhere, around some star, in a disk of gas and dust that collapsed and flattened and eventually gave rise to planets. This is the fundamental process of planetary system formation, repeated across the galaxy wherever molecular clouds fragment and young stars ignite. The disk cools as it spreads, and in the cooler outer regions, water and other volatiles condense into ice, coating dust grains, sticking together, building up into larger and larger aggregates. In the inner regions, close to the star where temperatures remain high, only rocky material can survive. Silicates, metals. Refractory compounds, these become the seeds of terrestrial planets. But farther out, beyond a threshold called the snow line where water can freeze, the available mass increases dramatically. Ice is abundant in the protoplanetary disk, far more abundant than rock. The planetesimals that form here grow quickly, and some grow large enough to begin capturing gas from the surrounding nebula, swelling into gas giants planets like Jupiter and Saturn, with massive atmospheres of hydrogen and helium surrounding cores of rock and ice. These giant planets are architects of chaos. Their gravity dominates the outer disk, scattering smaller objects, perturbing orbits, flinging planetesimals inward toward the star or outward toward the edge of the system. Some planetesimals collide and merge, building up the cores of the giants themselves. Others are ejected entirely, accelerated to velocities that exceed the escape velocity of the system, cast into interstellar space as permanent exiles. This is how 3i Atlas likely began its journey. A close encounter with a giant planet, perhaps during the violent early phase of planetary system formation, when orbits were still shifting and settling. The gravitational slingshot accelerated it beyond the reach of its parent star, and it drifted outward, cooling as it went, until it was no longer part of any system, a rogue, a wanderer, alone. Only took one gravitational shove to turn a comet into an interstellar traveller for millions of years. The timing of ejection is difficult to constrain, but it almost certainly occurred early, within the first few tens of millions of years after the star formed. This is when planetary systems are most dynamic, when giant planets are still migrating, when residual planetesimals are most numerous. After this period, the system settles into a more stable configuration. Ejections still occur, but at a much lower rate. The bulk of the interstellar population, the comets and asteroids now drifting through the galaxy, were likely ejected during this early chaotic phase. The parent star of 3I Atlas is unknown and likely unknowable. It could be any of the hundreds of thousands of stars within a few hundred light-years of the Sun. It could be older or younger, larger or smaller, hotter or cooler. It could be a solitary star or part of a binary system. It could still exist in much the same form as when 3I Atlas was ejected, or it could have evolved, expanding into a red giant or collapsing into a white dwarf. There is no way to trace the trajectory back with sufficient precision to identify the source, but the ejection itself leaves clues. The velocity of 3I Atlas, relative to the local standard of rest, is modest, a few dozen kilometers per second. This is consistent with ejection by a Jupiter-mass planet in a typical planetary system. A more massive planet or a closer encounter would have imparted a higher velocity. A less massive planet or a more distant encounter would have resulted in a lower velocity, possibly not enough to escape. The observed velocity sits in a narrow range that implies a specific kind of dynamical interaction, one that is common in the final stages of planetary system assembly. The process is not gentle. Planetesimals that are ejected often pass very close to the giant planet, within a few planetary radii, where the tidal forces are strong. These forces can heat the object through friction, squeeze and stretch it, potentially triggering outgassing or even fragmentation. Whether 3I Atlas experienced such stresses is unknown, but if it did, the effects would have been transient. Once ejected into interstellar space, the object cooled rapidly, and any internal heat would have dissipated over thousands of years, leaving no lasting trace. The architecture of planetary systems, it turns out, is inherently lossy. Not all of the material in the protoplanetary disk ends up in planets. Much of it is ejected, either by the giant planets or by interactions with nearby stars during the system's early years. Estimates suggest that for every kilogram of material that remains in a mature planetary system, several kilograms were lost scattered into interstellar space, or pushed inward toward the star, where it either accreted onto the star itself or evaporated in the stellar wind. Only took billions of solar systems forming and shedding debris to populate the galaxy with wanderers. This means the interstellar population is vast. Current estimates, based on the detection rate of objects like Oumuamua, Borisov, and 3I Atlas, suggest that there are trillions of interstellar objects larger than a few hundred meters in diameter drifting through the Milky Way. Most are comets' icy bodies ejected from the outer regions of their parent systems. Some are asteroids' rocky or metallic objects from the inner regions, ejected by more complex dynamical interactions. A small fraction may be planetary fragments, pieces of larger bodies that were disrupted by collisions or tidal forces. These objects constitute a kind of galactic ecosystem, a population that is constantly being replenished by new ejections from young planetary systems and gradually depleted by collisions, by accretion onto stars or planets, by the slow erosion of cosmic rays and interstellar gas. The timescale for this turnover is enormous, billions of years, but the process is ongoing. The galaxy is not static, it is dynamic, constantly rearranging its matter on every scale. 3I Atlas is a product of this process. It was created by planetary formation, shaped by gravitational interactions, and then discarded, left to wander. Its journey is not unique. It is one of countless similar journeys, most of which will never be observed, never intersect with another star closely enough to produce detectable activity. It is, in a sense, ordinary, a typical member of a vast, invisible population, but from the perspective of Earth, from the perspective of the few hundred astronomers tracking its motion and analysing its spectrum, it is extraordinary. It is a visitor, a messenger, a sample of material from beyond. It is something that can be studied, however briefly, however incompletely, and in that study lies the possibility of learning not just about this one object, but about the population it represents, about the processes that create and distribute matter across the galaxy, about the architecture of planetary systems that may be radically different from our own. The ejection of 3I Atlas was, in its time, a violent event, but it occurred millions of years ago in a system that is now distant and unknown. The violence has long since dissipated. What remains is the consequence an object in motion, carrying within it the record of that event, drifting through space until it encountered, by chance, another star. And here it is, warming in the sun's light, releasing gas and dust, briefly visible, before it returns to the cold and the dark, resuming the journey that was interrupted, however briefly, by its passage through the inner solar system. The galaxy is not composed solely of stars and their planets. Between the luminous points of stellar systems lies a vast, diffuse population of debris-rogue planets, comets, asteroids, fragments of larger bodies, all drifting through the interstellar medium, unbound to any star. This population is invisible in the conventional sense. The objects do not shine. They are too small and too cold to emit detectable thermal radiation. They reflect no light, or so little that they cannot be distinguished from the background. They exist in a state of permanent darkness, known only through inference and statistical modelling. Estimates of the total mass in this interstellar debris field are uncertain, but they are not negligible. Some models suggest that the mass of rogue objects in the galaxy could rival the mass contained in all the stars and planets combined. Others place the figure lower, but still significant, perhaps 10% of the galaxy's baryonic matter, wandering freely rather than locked into gravitational systems. The exact value depends on assumptions about the ejection rate from planetary systems, the efficiency of gravitational scattering, and the survival rate of objects over billions of years. What is clear is that ejection is common. Every star that forms a planetary system sheds material. The process is not optional. It's a consequence of the way planets form, the dynamical interactions that occur as a disk of planetesimals condenses into a smaller number of larger bodies. Conservation of momentum requires that for every object that moves inward, another moves outward. For every planet that settles into a stable orbit, dozens or hundreds or thousands of smaller objects are flung away. Most of these ejected objects are small kilometers or less in diameter, the size range of comets and asteroids, but some are larger. Simulations of planetary system formation suggest that rogue planets, worlds that were ejected entirely from their parent systems, could be common. These are not failed stars, not brown dwarfs, but objects that formed in a protoplanetary disk and were subsequently scattered by gravitational interactions with other planets. They drift through the galaxy as isolated worlds, carrying with them atmospheres, surfaces, possibly even subsurface oceans, but no star to warm them. Only took the mathematics of orbital dynamics to realize that most worlds born in planetary systems are eventually discarded. The detection of these rogue planets is challenging but not impossible. A few have been found through direct imaging isolated objects with masses between 1 and 10 times that of Jupiter, too young and too hot to have cooled entirely, still glowing faintly in the infrared. But these represent the most massive, youngest, and brightest members of the population. Older rogue planets, or smaller ones, are essentially undetectable with current technology. They can only be found if they happen to pass in front of a background star, producing a brief gravitational microlensing event, a temporary brightening, as the rogue planet's gravity bends and focuses the starlight. Microlensing surveys have detected hints of such objects, events that are consistent with free-floating planets drifting through the galactic disk. The statistics suggest that rogue planets could be as common as stars, or even more common, though the uncertainties are large. If true, this would mean there are billions of rogue worlds in the Milky Way, adrift in the space between stellar systems, cold and dark and utterly alone. 3i Atlas is not a rogue planet, but it is part of the same ecosystem. The processes that eject comets are the same processes that eject planets. The difference is one of scale, not of kind. A close encounter with a Jupiter-mass planet can fling a comet out of the system entirely. A close encounter between two forming giant planets can eject one of them, leaving the other in a stable orbit. Both outcomes are predicted by the same gravitational interactions, the same chaotic dynamics that characterize the early evolution of planetary systems. The galactic debris field is not uniformly distributed. It is densest in the plane of the galactic disk, where most stars are located and where the rate of planetary system formation is highest. It thins out above and below the plane in the galactic halo, though objects can reach these regions if they are ejected with sufficient velocity, or if their trajectories are perturbed by encounters with other stars. The distribution is also clumpy, reflecting the fact that stars form in clusters and associations, which produce localized bursts of ejections before the clusters disperse. Over time, the debris mixes. Objects ejected from one star system drift through the galaxy, potentially passing through the gravitational influence of other stars, some of which may capture them temporarily or deflect them onto new trajectories. The mixing timescale is long, hundreds of millions of years, comparable to the orbital period of the Sun around the galactic center, but it is not infinite. Eventually, the debris from different stars becomes indistinguishable, a homogenized population that has lost all memory of its origins. Only took a galaxy full of time to erase the signatures of individual births. The existence of this population has implications for the chemistry of the galaxy. Interstellar objects carry with them the molecules and isotopes that were present in their parent systems, including organic compounds, water, and other volatiles. When these objects collide with planets or are accreted by stars, they deliver this material, potentially seeding new systems with chemistry that originated elsewhere. This process, the transport of material between star systems via rogue objects, is a form of panspermia, though not in the biological sense. It is chemical panspermia, the mixing of molecular inventories across the galaxy. Whether this process is significant depends on the rate at which interstellar objects are captured by planetary systems. Most pass through without interacting. Their velocity is too high and their trajectories too far from any planet to result in capture. But occasionally, an object passes close enough to be deflected into a bound orbit, or to collide directly with a planet or moon. The impact rates are low, perhaps one significant collision per planetary system per 100 million years, but over the age of the galaxy, the cumulative effect could be substantial. 3i Atlas, if it were on a slightly different trajectory, could have been captured. A close encounter with Jupiter, with the right geometry and timing, could have deflected it into an elliptical orbit around the Sun, turning it from an interstellar visitor into a permanent resident of the solar system. This has almost certainly happened in the past. Some of the comets now orbiting in the Oort cloud, the distant reservoir of icy bodies that surrounds the solar system, may have originated in other star systems and were captured during close encounters billions of years ago. Distinguishing captured interstellar comets from native ones is difficult, because the act of capture erases much of the information about the original trajectory. But 3i Atlas will not be captured. Its velocity is too high, its trajectory too far from the massive planets that could alter it. It will pass through, sample the warmth of the Sun for a brief period, and then depart, returning to the interstellar medium from which it came. It will rejoin the vast, invisible population of debris, carrying with it the memory of a brief encounter that it has no means of recording. The galactic ecosystem of debris is not static. It evolves slowly, as new objects are ejected and old objects are destroyed or captured. The population today is not the same as it was 1 billion years ago, and it will not be the same 1 billion years from now. But the processes that maintain it, planetary formation, gravitational scattering, The occasional capture or collision are ongoing, and they ensure that the space between stars is never truly empty, only dark. The Sun's gravity begins to affect 3I Atlas long before the comet becomes visible. Gravity is not a force that switches on at some threshold distance. It extends infinitely, weakening with the square of distance but never vanishing entirely. At the edge of the solar system, tens of thousands of astronomical units from the Sun, the gravitational pull is faint, barely distinguishable from the collective influence of nearby stars, but as 3I Atlas drifts inward, crossing the heliopause where the solar wind meets the interstellar medium, the Sun's gravity begins to dominate. The trajectory bends, not sharply, not suddenly, but in a smooth, continuous curve. The comet's velocity vector rotates, its direction changing while its speed relative to the Sun increases. This is not propulsion. The comet is not accelerating in the conventional sense of a rocket burning fuel. It is simply falling, converting gravitational potential energy into kinetic energy as it descends into the Sun's gravitational well. The mathematics of this descent are elegant. The trajectory is a conic section, a hyperbola, defined entirely by the comet's initial velocity and the Sun's mass. No other forces are needed, at least not initially. The path is deterministic, predictable, a solution to equations that have been understood for centuries, given the position and velocity at any one moment. The position and velocity at any other moment can be calculated with arbitrary precision, limited only by the accuracy of the input data. But the Sun cannot hold 3I Atlas. The comet's velocity, even at its slowest point, the perihelion, the closest approach to the Sun will still exceed the escape velocity at that distance. The hyperbola does not close. The trajectory bends inward, reaches a minimum distance, then opens outward again, carrying the comet back toward the edge of the solar system and beyond. The encounter is transient. The Sun's gravity deflects the comet, alters its direction, but cannot capture it. Only took crossing half the solar system to be touched by a star and then released. The perihelion distance of 3I Atlas is not yet precisely known. It depends on details of the trajectory that are still being refined as more observations accumulate. But current estimates place it somewhere between the orbits of Earth and Venus, perhaps as close as 0.7 astronomical units from the Sun closer than Earth, but not dramatically so. At this distance, the solar heating will be intense, the surface temperature of the nucleus rising above the sublimation point of water ice, driving vigorous outgassing and potentially causing structural changes or fragmentation. The comet will not linger at perihelion. The geometry of hyperbolic orbits is such that the closest approach occurs at a single moment, a point in time that lasts for seconds or minutes depending on the scale of the measurement, before and after this moment. The comet is receding, the distance increasing, the influence of the Sun's gravity diminishing. The entire passage through the inner solar system from the orbit of Jupiter inward, around the Sun, and back out to Jupiter's orbit will take only a few months. Compared to the millions of years spent in interstellar space, this is an eye blink. From the comet's perspective, if such a perspective could exist, the Sun is a temporary disturbance, a source of warmth that rises and then fades, a gravitational well that pulls and then releases. The comet has no awareness of the event, no memory that it is passing through a planetary system, no knowledge that it is being observed. It simply follows the trajectory determined by its velocity and the gravitational field it finds itself in, responding to forces with perfect obedience but no comprehension. The bending of the trajectory is not unique to 3I Atlas. Every object passing through the solar system experiences the same effect. Asteroids, comets, spacecraft all have their paths bent by the Sun's gravity. The difference is that bound objects, those with elliptical orbits, return. The Sun captures them not in space but in time, pulling them back again and again in an endless loop. Unbound objects, like 3I Atlas, pass through once and are gone. The deflection angle, the total change in direction caused by the gravitational encounter, depends on the perihelion distance and the velocity. A closer approach results in a sharper bend. A higher velocity results in a smaller deflection. For 3i Atlas, the deflection will be significant, perhaps 30 or 40 degrees, enough to send the comet off in a substantially different direction than it was travelling when it arrived. This new direction is not random. It is determined entirely by the geometry of the encounter, and it can be calculated with precision once the orbit is fully known. Only took the curvature of space-time to change a trajectory set millions of years ago. The Sun's gravity is not the only force acting on the comet, though it is by far the strongest. The gravitational influence of the planets also plays a role, particularly Jupiter, whose mass is large enough to perturb the orbits of passing objects, even at considerable distances. If 3i Atlas passes reasonably close to Jupiter, within a few tenths of an astronomical unit, the planet's gravity will add a small additional deflection to the trajectory. This is the same mechanism that allows spacecraft to perform gravity assists, using a planet's motion to gain or lose velocity relative to the Sun. For 3i Atlas, any such encounter will be distant and the effect small. The comet's trajectory does not bring it close to any of the major planets. It threads through the inner solar system on a path that avoids the massive bodies, influenced primarily by the Sun itself. The planets are almost irrelevant. Their gravitational perturbations measurable, but not significant in determining the overall shape of the orbit. There is also the effect of outgassing, the so-called non-gravitational forces that arise when a comet releases jets of gas and dust. These jets exert a small thrust on the nucleus, pushing it in the direction opposite to the escaping material. For an active comet, this thrust can be significant enough to measurably alter the trajectory, causing deviations from the purely gravitational path. The effect accumulates over time, and for long-period comets that remain active for months or years, the cumulative deviation can amount to thousands of kilometers in position, or several meters per second in velocity. For 3i Atlas, the magnitude of this effect depends on how active the comet becomes. If the outgassing is vigorous, the non-gravitational forces will be noticeable, and they will need to be included in the orbital models to accurately predict the comet's future position. If the outgassing is weak, the effect may be negligible. Lost in the uncertainties of the gravitational calculation, the answer will emerge from the data, from the comparison of observed positions to predicted positions, from the residuals that remain after the gravitational model has been fitted. So far, the observations suggest that 3i Atlas is active, but not exceptionally so. The coma is present, the brightness is increasing, but there are no reports of dramatic outbursts or unusual behaviour. The trajectory, as currently determined, does not show large deviations from the gravitational prediction, but the comet is still approaching perihelion, still warming, and the level of activity may increase. The final answer will not be known until after the comet has passed and receded, until the full arc of the trajectory has been observed and analysed. The Sun's hold on 3i Atlas is brief and temporary. A few months of interaction, a bending of the path, a warming of the surface, and then release. The comet will depart carrying slightly less mass than it arrived with, having shed ice and dust during its passage, but otherwise it will be unchanged. The encounter will leave no lasting mark, no permanent alteration. It will simply be an event, a perturbation in an otherwise straight-line trajectory through the galaxy, significant only in the sense that it made the comet visible, briefly, to the inhabitants of one small planet orbiting the star it passed. Locked within the ice of 3i Atlas are molecules that have not interacted with the Sun's radiation, have not been processed by solar wind, have not been altered by any influence originating from our star. They are pristine in a way that few materials in the solar system can claim to be. Even the most primitive meteorites, even the samples returned from asteroids and comets by spacecraft, have been modified to some degree by collisions, by exposure to cosmic rays, by the slow accumulation of impacts over billions of years. But the interior of 3i Atlas, The ice that has not yet sublimated remains as it was when it formed. This ice contains water, certainly, but not only water. Spectroscopic observations suggest the presence of carbon-bearing molecules, carbon monoxide, carbon dioxide, perhaps methane or more complex organics. These species are common in comets, but their relative abundances vary, and those variations encode information about the temperature and pressure at which the ice condensed. A high abundance of carbon monoxide, for example, suggests formation at very low temperatures, below about 30 Kelvin, where carbon monoxide can freeze out of the gas phase. A lower abundance suggests warmer conditions, where carbon monoxide remains gaseous and escapes before being incorporated into the ice. The isotopic composition of the molecules is even more informative. Isotopes are atoms of the same element with different numbers of neutrons chemically identical, but with slightly different masses. The ratios of these isotopes in a sample reflect the processes and environments through which the material has passed. Deuterium, the heavy isotope of hydrogen, is particularly valuable. The ratio of deuterium to ordinary hydrogen in water ice depends on the temperature at which the ice formed, and on the history of chemical reactions that occurred in the gas phase before freezing. In the solar system, the deuterium to hydrogen ratio in water varies slightly from object to object. Comets tend to have higher ratios than the Earth's oceans, though there are exceptions. This has led to debates about whether comets delivered the water that now fills Earth's oceans, or whether the water came from another source asteroids, perhaps, or material that was already present in the inner solar system when Earth formed. The question remains unresolved. Only took 4.5 billion years of planetary evolution to still be uncertain where the oceans came from. For an interstellar comet like 3I Atlas, the isotopic ratios may be different. The molecular cloud in which it formed, the star around which it condensed, the specific conditions of temperature and radiation, all of these could have been different from those in the solar nebula. If the differences can be measured, they provide a direct comparison between the chemistry of two stellar systems, a glimpse into the diversity of planetary formation environments across the galaxy. But measuring isotopic ratios remotely is extraordinarily difficult. The spectral lines of deuterated molecules, molecules in which one or more hydrogen atoms have been replaced by deuterium, are faint and often blended with stronger lines from the more common isotopologues. Detecting them requires high spectral resolution, long integration times, and observations at specific wavelengths that are often absorbed by Earth's atmosphere. Space-based telescopes are ideal, but they are heavily oversubscribed, and time on such instruments is allocated competitively. There is no guarantee that 3I Atlas will receive the necessary observations. If the data can be obtained, the analysis will still be challenging. The observed ratios in the coma are not necessarily the same as the ratios in the nucleus. Photodissociation, chemical reactions in the coma, and preferential sublimation of lighter molecules can all alter the isotopic composition of the gas. Models are needed to account for these processes, and those models carry their own uncertainties. The dust grains lifted from the surface by outgassing also carry information. These grains are not pure ice, but a mixture of ice and refractory material silicates, carbonaceous compounds, perhaps metals. The composition of this refractory component reflects the solid material that was present in the protoplanetary disk, material that condensed at high temperatures close to the forming star and was later mixed outward into the colder regions where comets form. The silicate grains in particular are of interest. Their mineralogy, the specific crystal structure and chemical composition, depends on the temperature at which they condensed, and on any subsequent heating or alteration. Some silicates are amorphous, lacking any long-range order, indicating that they condensed rapidly or were never heated enough to crystallize. Others are crystalline, with well-defined structures, indicating exposure to higher temperatures, either during formation or later through processes like shocks or transient heating events. Observations of solar system comets have revealed a mix of amorphous and crystalline silicates, with the proportions varying from comet to comet. The origin of the crystalline component is debated. Some may have formed in the hot inner regions of the solar nebula and been transported outward by turbulent mixing. Others may have been produced by transient heating events, brief flashes of high temperature caused by shocks in the disk, or by localized heating from energetic particles. Only took the invention of infrared spectroscopy to realize that comet dust remembers temperatures it should never have experienced. For 3I Atlas, the silicate composition remains unknown. Infrared observations, if they can be obtained, might reveal the characteristic spectral features of crystalline silicates, sharp peaks at specific wavelengths, corresponding to the vibrational modes of the crystal lattice. The presence or absence of these features, and their relative strengths, would provide clues about the thermal history of the dust, and by extension, about the conditions in the protoplanetary disk where the comet formed. The organic compounds in the ice are another unknown. Comets are known to contain a rich inventory of organic molecule species ranging from simple 2-carbon compounds like ethane to complex prebiotic molecules like amino acids. These organics are formed by chemical reactions in the gas phase of the molecular cloud, by reactions on the surfaces of dust grains, and by radiation processing of ices in the outer regions of the protoplanetary disk. They are not life, but they are the building blocks from which life could potentially emerge, given the right conditions. Whether the organic inventory of 3I Atlas differs from that of solar system comets is an open question. The basic chemistry reactions involving hydrogen, carbon, nitrogen, and oxygen should be similar, because these elements are abundant throughout the galaxy, and their chemical behavior is governed by universal physical laws. But the details may vary. The abundance of specific molecules, the ratios of isomers, the degree of complexity all could differ depending on the local environment, the radiation field, the timescales involved. Detecting and characterizing these organics remotely is difficult. Many organic molecules do not have strong spectral features at the wavelengths accessible to ground-based telescopes. They are better studied in the infrared or at millimeter wavelengths, where molecular rotations and vibrations produce distinctive lines. But again, access to the necessary instruments is limited, and the comet's brightness may not be sufficient for detailed spectroscopy. What is clear is that 3I Atlas is a repository of information. Every molecule, every isotope, every grain of dust carries a piece of the story of where it came from, how it formed, what conditions prevailed in the disk around another star. The challenge is extracting that information, decoding the signals, separating the original composition from the alterations caused by millions of years in interstellar space and the more recent heating as the comet approaches the Sun. The opportunity is brief. The comet will not wait for better instruments or clearer weather. It will pass through, release what it releases, and depart. And what it carries with it, the unobserved molecules, the unmeasured isotopes, the dust that was not captured will remain unknown, sealed again in ice, invisible, unreachable, drifting back into the galaxy from which it came. The detection of 3I Atlas is, in part, a consequence of improved technology. The telescopes that found it automated survey instruments scanning the sky night after night, comparing images, flagging anything that moves did not exist a generation ago. The sensitivity of modern digital cameras, the computational power to process vast quantities of data, the algorithms that distinguish real objects from artifacts and noise, all of these are recent developments, refined over the past few decades to the point where detecting faint, fast-moving objects has become routine rather than exceptional. But the detection rate is still low. 3 confirmed interstellar objects in 7 years suggests that such visitors are not rare in an absolute sense, but they are rare relative to the number of solar system objects that are detected. For every interstellar comet like 3I Atlas, thousands of ordinary comets and asteroids are discovered. The interstellar population is simply harder to find. The objects are moving faster. They are often fainter, and the window for detection is brief. This will change. The next generation of survey telescopes, instruments like the Vera-C, Rubin Observatory, currently under construction in Chile, will increase the detection rate by orders of magnitude. Rubin Observatory will scan the entire visible sky every few nights, imaging billions of stars and galaxies, and in the process detecting everything that moves: asteroids, comets, distant planets, and yes, interstellar visitors. Projections suggest that once Rubin is operational, interstellar objects could be detected at a rate of several per year, or even per month, depending on the true abundance of such objects in the galaxy. This shift from rare to routine will transform the field. Instead of scrambling to observe a single object during its brief passage, astronomers will have access to multiple objects at any given time, allowing for comparative studies, for the identification of patterns and trends, for the statistical analysis that is currently impossible with a sample size of 3. The questions that remain unanswered about 3I Atlas, its composition, its structure, its place in the larger population will begin to be addressed not through the intensive study of individual objects, but through the collective properties of dozens or hundreds. Only took 100 years of astrophotography to finally build instruments fast enough to catch what has always been passing through. Other observatories will contribute. Space-based telescopes, free from the distortions and absorptions of Earth's atmosphere, will provide spectroscopy at wavelengths that are inaccessible from the ground. Infrared observatories will characterize the dust and measure the thermal emission from nuclei. Ultraviolet instruments will detect the signatures of highly volatile species like carbon monoxide. Radio telescopes will search for the emission lines of molecules in the coma, providing complementary data to optical and infrared observations. The coordination of these observations is not trivial. Each telescope has its own schedule, its own queue of approved programs, its own technical constraints. Observing an unexpected target like an interstellar comet requires flexibility, the ability to interrupt planned observations and redirect instruments quickly. Not all observatories can accommodate this. Not all observers are willing to sacrifice their allocated time. The result is that some opportunities are missed, some data is not collected, and the final data set, when the observations are complete, is inevitably incomplete. But the future promises improvement. As interstellar objects become more common in the observational record, the process of coordinating observations will become more streamlined. Templates will be developed, protocols established, rapid response networks activated. The improvisation and ad hoc arrangements that characterize the current observations of 3I Atlas will give way to a more systematic approach, one designed to maximize the scientific return from each detection. There is also the possibility of missions, not to 3I Atlas, which is already too far along in its trajectory and moving too fast for any currently available spacecraft to intercept, but to future interstellar visitors. Concepts exist for rapid response spacecraft that could be launched on short notice, accelerated by powerful rockets or even solar sails, and sent on intercept courses to study interstellar objects up close. Such missions would be expensive and technically challenging, but the scientific payoff would be enormous. A spacecraft could resolve the nucleus, measure its size and shape directly, analyze the composition of the coma with in situ instruments, and perhaps even land on the surface or return a sample to Earth. These are not fantasies. They are engineering problems, difficult but not impossible, constrained more by funding and political will than by the laws of physics. The detection of Oumuamua sparked serious discussions about the feasibility of such missions, and several proposals have been developed, though none have been funded. The continued detection of interstellar objects and the growing recognition of their scientific importance may eventually tip the balance. It may take a decade, or 2, or 3, but it is plausible that within the lifetimes of people currently working in the field, a spacecraft will visit an interstellar comet. Only took the third visitor to make interstellar missions seem inevitable rather than aspirational. In the meantime, ground-based and space-based observations will continue to improve. Adaptive optic systems, which correct for the blurring effects of Earth's atmosphere in real time. are becoming more capable, allowing ground-based telescopes to achieve resolutions that approach those of space-based instruments. New detector technologies are increasing sensitivity, reducing noise, extending the wavelength range over which observations can be made. Advances in spectroscopy are enabling the detection of fainter lines, the measurement of weaker signals, the extraction of more information from each photon of light. The computational tools are also advancing. Machine learning algorithms are being developed to identify interstellar objects automatically, distinguishing them from the far more numerous solar system objects based on their orbital characteristics and kinematics. These algorithms can sift through vast data sets, flagging candidates for follow-up observation, reducing the time between detection and confirmation. They are not perfect false positives, and false negatives occur, but they are improving, and they will become an essential part of the discovery process as the volume of data continues to grow. The trajectory of the field is clear. Interstellar objects, once considered exotic rarities, are becoming a standard part of the astronomical landscape. The tools to detect them, to study them, and eventually to visit them are being developed. The questions they raise about the diversity of planetary systems, about the transport of material across the galaxy, about the commonality or uniqueness of the solar system's formation, will be answered, not quickly, but incrementally. As the sample size grows and the quality of the data improves, 3i Atlas is part of this transition. It is not the first, and it will not be the last. It is one data point in a dataset that is just beginning to grow, one object in a population that is just beginning to be characterized, the observations being made now, the spectra being collected, the orbital elements being refined. All of this will be compared to the data from future objects, and from that comparison, patterns will emerge, trends will be identified, and the nature of the interstellar population will begin to come into focus. The future observatories will see what is passing through now but going unnoticed. They will see the faint distant objects that are too far from the sun to outgas, too small to reflect much light, too fast to be tracked by current instruments. They will see the population as it truly is, not just the brightest and most active members, but the full distribution, the large and the small, the icy and the rocky, the fresh and the ancient. And in seeing that population, they will reveal the architecture of the galaxy in a new way, not as a collection of isolated star systems, but as a connected web, a dynamic system in which matter is constantly being exchanged, redistributed, and recycled. The debris field is not a static backdrop. It is an active participant in the evolution of the galaxy, and the interstellar objects passing through the solar system are messengers from that larger system, carrying information that cannot be obtained in any other way. The departure of 3i Atlas will not be sudden. It will not vanish in a moment, will not blink out of existence once it passes perihelion. Instead, it will fade gradually, a slow diminishment that mirrors, in reverse, the brightening that occurred during its approach. The outgassing will decline as the comet recedes from the sun, as the surface temperature drops, as the sublimation of volatiles slows and then ceases. The coma will shrink, the tail will dissipate, the brightness will fall. For a time, the comet will remain visible to large telescopes. Observations will continue as long as the signal is strong enough to distinguish from the background noise of the sky. Astronomers will track its position, refining the orbital elements, watching for any late surprises, outbursts, fragmentation, deviations from the predicted trajectory. But eventually, the comet will become too faint. The exposure times needed to detect it will grow impractically long. The signal-to-noise ratio will drop below the threshold for reliable measurement, and at some point, the last observation will be made, the final data point collected, and 3i Atlas will fade from view. The direction of its departure is already determined. The hyperbolic trajectory, bent by the sun's gravity, carries the comet outward toward a specific point on the celestial sphere, a direction that will not change significantly as it recedes. Current calculations suggest the comet is heading toward the constellation Lynx, a faint and relatively obscure region of the northern sky, named not for any prominent stars but for the fact that one must have the eyes of a lynx to see it clearly. The name is fitting, in a way, for a destination that will itself become invisible. The comet will not reach Lynx quickly, of course. Constellations are human constructs, patterns imposed on stars that are at vastly different distances. Lynx is not a place, but a direction, and the comet will continue in that direction for millions of years, long after the stars that define the constellation have drifted into new configurations. The galaxy rotates, the stars orbit, the patterns change. By the time 3i Atlas has travelled far enough for the constellation Lynx to be meaningfully behind it, Lynx will no longer exist as a recognisable pattern. Only took the invention of constellations to give us a way to describe where things are going that will no longer exist when they get there. As 3i Atlas recedes, it will accelerate back toward the velocity it had when it arrived. The energy it borrowed from the sun's gravitational well during its inward fall will be returned during the outward climb. The exchange is perfectly reversible, at least in the gravitational sense. The comet will exit the solar system with almost exactly the same kinetic energy it had when it entered, though the direction will be different, altered by the gravitational deflection. There is, however, a small asymmetry. The comet has lost mass during its passage, shedding ice and dust through outgassing. This mass loss, though a tiny fraction of the total, has a measurable effect. The comet is lighter now than when it arrived, and a lighter object, given the same kinetic energy, moves slightly faster. The effect is small, perhaps a few meters per second, but it is real, and it represents a permanent change. The comet that departs is not quite the same comet that arrived. The tail, if one formed during the peak of activity near perihelion, will point in a different direction during the outward journey. Near the sun, the tail pointed away from the sun, pushed by radiation pressure and the solar wind. But as the comet recedes, the tail may lag behind, a diffuse trail of dust and gas that slowly disperses into the interplanetary medium. This material will not follow the comet. It will remain in the solar system, orbiting the sun on trajectories determined by the point at which it was released. Some of it may eventually fall back onto the sun. Some may be swept up by planets or moons. Most will simply drift, becoming part of the zodiacal dust cloud, the faint glow of scattered sunlight that can be seen from Earth on dark, moonless nights. The molecules released into the coma will also remain behind. Water, carbon monoxide, methanol, and dozens of other species, now photo-dissociated into fragments, will continue to travel outward on their own trajectories, gradually mixing with the solar wind and the ambient interplanetary medium. Within weeks or months, these molecules will be indistinguishable from the background, their origin forgotten, their connection to the comet erased. Only took one passage near a star to leave behind a chemical signature that will outlast the memory of what created it. The observations will continue as long as possible, but they will become less frequent. The urgency that characterized the early weeks, the competition for telescope time, the coordination of observations across multiple facilities, all of this will relax as the comet fades and the primary scientific questions are addressed. Some observers will continue to track it, motivated by completeness, by the desire to extend the orbital arc as far as possible, by the hope that something unexpected might still occur. But the number of observations will decline, and eventually they will cease altogether. When the last observation is made, when the final image is taken and the final spectrum is recorded, the comet will not stop existing. It will simply stop being observable. It will continue on its trajectory, receding from the sun at tens of kilometers per second, cooling as the distance increases, returning to the dormant state it maintained for millions of years before entering the solar system. The ice will refreeze, if any was melted. The surface will stabilize. The rotation will continue, unchanged, and the comet will drift back into the interstellar medium, invisible once again. The trajectory will take it past other stars, eventually. Not soon the nearest stars are light years away, and at its current velocity, 3i Atlas will not approach another stellar system for tens or hundreds of thousands of years. But the galaxy is patient. The comet will drift, and in time it will wander close enough to another star to feel its gravitational pull, to have its trajectory bent again, perhaps even to be warmed again. If the approach is close enough, the cycle could repeat, though the likelihood of any given object passing through multiple stellar systems in a way that makes it observable is vanishingly small. More likely, 3i Atlas will simply continue drifting, one object among trillions, invisible and unobserved, travelling through the galaxy indefinitely. It will not decay, it will not evaporate, barring a collision, which is improbable, or capture, which is also improbable. It will exist in essentially its current form for billions of years, a frozen archive of the conditions in which it formed, accessible to no one, observed by no one, carrying information that will never be retrieved. The departure is already underway. The comet is past perihelion now, or will be soon, depending on when these words are read. It is receding, cooling, fading. The observations are winding down. The data is being analysed. The story is being written, or at least the part of the story that can be told with the observations that were made. The rest of the story, the part that happens after the comet, becomes invisible, after it leaves the solar system, after it returns to the void, will go unwritten. It will simply happen, unobserved, in the vast darkness between stars. What remains, after the comet has faded from view, is data, not the comet itself, which continues to exist but is no longer accessible, but the record of its passage, the images, the spectra, the photometric measurements, the astrometric positions. These are stored in digital archives, in databases maintained by observatories and research institutions, in the supplementary materials of published papers. They are numbers, mostly columns of values representing brightness at different times, wavelengths and their corresponding intensities, celestial coordinates measured to fractions of an arc-second. The data is not raw experience. It is abstraction, translation, a conversion of photons into electrons into bits, a chain of transformations that renders the physical event light from a distant comet striking a detector into a form that can be transmitted, stored, analysed, and compared. The comet itself is not in the data. What is in the data is a shadow, a projection, a representation that captures certain properties while inevitably losing others. But this is what remains. This is what can be studied after the event has passed, and from this data, carefully analysed, patterns can be extracted, models can be tested, questions can be answered. The brightness curve reveals the outgassing rate and its dependence on solar distance. The spectrum reveals the molecules present in the coma and, by inference, in the nucleus. The astrometric measurements reveal the trajectory, the velocity, the orbital elements, the direction from which the comet came, and the direction toward which it is going. The orbital elements, in particular, are preserved with high precision, the semi-major axis, which for a hyperbolic orbit is negative, indicating that the orbit does not close, the eccentricity, greater than 1, confirming the unbound nature of the trajectory, the inclination, the argument of perihelion, the longitude of the ascending node. All of these are recorded, along with their uncertainties, in standardized formats that allow them to be archived and retrieved decades or centuries later. Only took the motion of light across a sensor to encode the trajectory of something that travelled for millions of years. These orbital elements are not merely descriptive, they are predictive. Given the position and velocity of 3i Atlas at any moment during its passage through the solar system, the position and velocity at any other time can be calculated past or future, within the limits of the perturbations from outgassing and the uncertainties in the measurements. The comet's location a year from now, a decade from now, a century from now, exists as a calculation, a set of coordinates that can be derived from the stored data even though no observation will be made to confirm them. This predictive power is limited. Of course, the farther into the future the calculation extends, the larger the uncertainties become. Small errors in the measured velocity propagate, and after a certain point, the prediction becomes meaningless. But for timescales of decades or centuries, the trajectory can be known with reasonable confidence if, in the year 2124, an astronomer wanted to know where 3I Atlas was, the answer could be calculated from the data collected in 2024 and 2025, even though the comet itself would be far beyond the reach of any telescope. The spectroscopic data is different. It does not predict the future, but it encodes the past. The wavelengths of light absorbed or emitted by molecules in the coma reveal which molecules were present, and in what relative abundances. This, in turn, provides constraints on the composition of the ice, the temperature at which it formed, the environment of the protoplanetary disk or molecular cloud that gave rise to the comet. The data is indirect, filtered through models and assumptions, but it is the closest thing to a direct sample that will ever be obtained without a spacecraft mission. The images, too, are preserved, not moving images, not video, but still frames, each one a snapshot of the comet at a particular moment, seen from a particular angle, under particular conditions of illumination and observation. These images show the morphology of the coma, the presence or absence of jets, the structure of the tail if one was present. They are not high resolution. The comet is too distant and too small for that, but they capture the overall appearance, the distribution of light, the changes over time. Over the weeks and months of observation, hundreds or thousands of such images will accumulate. Each one is slightly different, reflecting the rotation of the nucleus, the changing distance from the Sun, the evolution of the outgassing pattern. Taken together, they form a time series, a record of how the comet changed during its passage through the inner solar system. This record is incomplete. Gaps appear whenever weather or scheduling prevented observations, but it is the most complete record that exists, and it is permanent. The images do not decay, they do not fade, they can be examined and re-examined, years or decades later, as new questions arise or new analysis techniques become available. Only took a few months of observation to create a permanent archive of something that will never be seen again. The data is not static, it is analysed, reanalyzed, compared to models, used to test hypotheses. Different researchers, approaching the same dataset with different questions or different assumptions, may extract different conclusions. This is not a flaw, but a feature. The data is the common ground, the shared reference, the thing that remains constant even as interpretations evolve. A spectrum collected in 2024 can be reanalyzed in 2034 or 2044. Using improved models of molecular photochemistry or better laboratory measurements of spectral line positions. The original observation does not change, but the information extracted from it can grow over time. There is also the possibility of comparison. When the next interstellar comet is detected, its data will be compared to the data from 3I Atlas, and from 2I Borisov, and from 1I Oumuamua. Similarities and differences will be noted, patterns will emerge, and the individual objects will begin to be understood not in isolation, but as members of a population. The data from 3I Atlas will contribute to this understanding long after the comet itself has become unobservable. In this sense, the data is a kind of persistence. The comet's physical presence in the solar system was brief, a matter of months, but its informational presence extends indefinitely. As long as the archives are maintained, as long as the data is accessible, 3I Atlas continues to exist in a form that can be studied, analysed, and compared. It is not the same as the comet itself, but it is not nothing. It is a trace, a residue, a record of an event that occurred and can never be repeated. The cataloguing is also important. 3I Atlas has been assigned a formal designation, a unique identifier that distinguishes it from all other objects. This designation will appear in databases, in publications, in lists of known interstellar objects. It is a small thing, a string of characters, but it ensures that the comet is not forgotten, that its passage is noted, that future researchers who encounter the data will know what they are looking at. The physical comet is receding, cooling, fading into invisibility, but the data remains. The orbital elements, the spectra, the images, the photometric measurements. All of these are stored, archived, preserved. They are what is left after the event has passed. They are the permanent record of something transient, the memory of an encounter that lasted only a few months but will be remembered in this form for as long as the archives endure, and in those archives, 3i Atlas takes its place alongside the other visitors, the other data points, the other fragments of the galaxy's vast, invisible population of wandering debris. It is one among many, or one among few, depending on how the counting is done, but it is recorded, it is known, and that, in the end, is what persists. The archives grow quiet. The data sits, arranged in rows and columns, in files with standardized names, in directories organized by date and object type. The comet itself is gone, or rather, it is elsewhere beyond the orbit of Neptune by now, or perhaps farther, depending on when this moment is. It no longer outgases, it no longer brightens. It has returned to the state it held for millions of years before entering the solar system cold, dark, inert, invisible. The telescopes that tracked it have moved on. They point toward other targets now, other comets, other asteroids, other galaxies, other mysteries. The observers have submitted their papers, archived their data, turned their attention to the next project, the next proposal, the next question. The urgency has passed. The moment of discovery, of observation, of frantic data collection before the object fades, that moment is over. What remains is stillness, not the absence of motion, because the comet continues to move, and the galaxy continues to turn, and the stars continue their slow drift through space. But the stillness of completion, the quiet that comes after an event, has ended and its echoes have faded. The comet came, was observed, and departed. The story, such as it is, has been told. Somewhere in the galaxy, there are other comets, other wanderers, drifting through the same darkness that 3i Atlas now re-enters. They are not being observed, they are not being tracked, they simply exist, moving on trajectories set millions of years ago, carrying ice and dust from places that will never be known, heading toward encounters that may or may not occur. The galaxy is full of such objects. The space between stars is not empty, only dark, and in that darkness, 3i Atlas drifts, no longer warming, no longer watched, simply travelling, as it has for so long, as it will for so long to come. The ice is frozen again, the surface is still, the rotation continues, unchanged. There is no sound, no light, no indication that anything has changed. The passage through the solar system, so significant to those who observed it, was to the comet itself only a brief perturbation, a momentary warming, an event that left no lasting awareness because there is no awareness to be left. Time passes, years, decades, centuries. The comet recedes farther and farther, its distance measured now in light years rather than astronomical units. It becomes part of the interstellar medium again, one object among countless others, invisible and unremarked. The data remains, but the observations cease. The last telescope that could have detected it no longer points in that direction. The last observer who thought of it has moved on or retired or passed away. The comet fades from active memory, persisting only in the archives, in the lists, in the records that are rarely consulted but never deleted. And still it drifts, through the long, slow rotation of the galaxy, through the shifting configurations of stars, through the vast, patient architecture of space and time, it does not hurry, it does not rest. It simply continues, as it has always continued, as it will always continue, until the universe itself grows cold and still, and the distinction between motion and stillness becomes meaningless. The story ends not with drama, but with distance, not with resolution, but with recession. The comet departs, the data persists, and the galaxy turns, slowly, under stars that will shine for billions of years yet, illuminating nothing in particular, observed by no one, simply existing as they have always existed, as they will continue to exist, long after the names we have given them have been forgotten. Sleep well.